Good morning and good afternoon to everyone who is here. We have a global audience, so there are different time zones. I want to welcome you to another WIDIA webinar today. My name is Isabel Milan and I'm from WIDIA Marketing and Communication Department. As WIDIA in these difficult times when more people are staying at home, we are offering a series of educational trainings and courses every week about the metal cutting arena. And today and also tomorrow, because tomorrow we'll have the second session, we are offering the turning application course. And I receive this question quite often. How do I receive information about WIDIA courses, webinars, or any other kind of activity? Please subscribe to our newsletter and you will receive them all. I just left the link in the chat for you. So how is the webinar going to be organized today? Our presenter, Vladimir, is the regional product manager for WIDIA. He has a lot of experience in the metal cutting arena. He also has a lot of experience in trainings and courses. And today he's going to do around 40 minutes presentation, and then the rest of the session is going to be dedicated to your questions. So please feel free to write your questions throughout the session in the questions panel. It can be found on the right side of the GoToWebinar tool, and you can open the panel with the orange arrow and go in the question section. You fill in the question and then you click enter, and we will answer it at the end of the session with Vladimir. Okay, so I think we are ready. One last thing, you will also receive a recording of the webinar in the next days. And you can also share it with your colleagues, with your customers, with anyone who may find it valuable. I also encourage you to share any other courses we may do in the future with them. So Vladimir, we are ready to start, and I wish you a great webinar.
Hello, dear metalworking colleagues. Let's talk together about turning about application. We have slightly big presentations with videos about our assortment, and you might know that we have slightly wide assortment for turning operations, for general turning and for cutting off, for parting and grooving, and also for threading, for everything what is needed generally. Also, you can find this information in our catalogs. But today we will talk about this application, how it's been done, and it's a more or less basic training, also with some tips. So we will talk about definitions, about geometries, and not only today, but also tomorrow. Today, maybe 50% we will pass, and the next day we will talk about cutting tool materials, workpiece materials, how to avoid wear, and so on. So different additional topics to the turning, which related to turning tools. So today we will talk about concept of turning, comparison of turning and milling in implementation, and also about geometrical components of turning cutters, like cutting angles, and also related to inserts, cutting inserts, and also about cutting forces. And in the end, we will talk about cutting data and cutting parameters, which influence on the cutting process, or also on effectiveness of cutting process. So at first, which types of turning operations you can face with? They can be different. So today and tomorrow we'll talk about general turning, but a lot of things they relate to other types of turning, like parting and grooving, for example, like a threading, like a heavy duty turning, and also other close to turning operations. Also, there can be different external and internal, depending on which kind of, from which side you want to machine the component, from outside or from inside. So it can be external or internal general turning, external, internal parting and grooving, threading also. As if to talk about general turning, it can be facing. You will see on the next slide, but I will try briefly to show it now. 1 second. So facing, when you need to machine the face of the operation. Also longitudinal turning, so it's just linear turning operation, and also they can be copying when we need to make a complex machine to complex shape from cylindrical workpiece. Also, there can be a trochoidal one when we use, for example, round shape of insert and machining of some sort of groove here by trochoidal trajectory. When we talk about parting and grooving, there can be usual parting and grooving. I mean, when we cutting material perpendicular to its axis, so we can part off it, or we can make a groove. Also, we can make a groove on face. This operation called face grooving, and also possible to use it like for general turning. This kind of tools for copying operations, for example. And threading can be, external and internal, and different type of passes can be used. I hope in additional webinars which are dedicated for parting and grooving and threading we will organize in future. We will talk deeper about what does it mean and how to program better your threading process, for example. So what is a turning process? Basically, it's a shaping process by metal cutting. When workpiece, it's a cylindrical workpiece. It's been rotated by a machine tool or lathe. For this operation was invented many years ago, and more or less modern ones known. They were developed in the beginning of 19th century in Great Britain. And so now we have a little bit more modern ones when in a chuck workpiece has been clamped, chuck and spindle has been rotated, and the cutting tool is coming up to the edge of a workpiece and going in the direction of feed, depending on which side we need to machine, face, cylindrical or back, and so on. So feed motion is done by tool, which is also clamped to, you can see here an elementary letter here. And cutting speed and cutting motion, main cutting motion is being generated by spindle, its rotation. So it's been done like it will be shown now here. It was a facing operation, now it's a longitudinal turning. There are also other types of operations for sure. It's tapping, milling, drilling, and so on. But the most popular ones are turning and milling. And what's the comparison? So milling cutter, in general, it's like a turning cutter, but with more tools. But not only, more teeth. But not only because it's like consisted of many turning cutters on here and many cutting edges. And also here in milling, main cutting motion is being done by a milling cutter, so by the tool. And the workpiece, usually it's a prismatic shape or cubic shape workpieces. They are they're moving by a table of the milling machine, for example. So If we talk about turning, it can be continuous or interrupted, but usually when you saw it on previous slide, cutting edge is constantly in a contact with workpiece material, with steel or cast iron or whatever. Basically, so in most of cases, cut is continuous, so it's constantly cut. It's deep inside this meat or this steel. While a milling cutter tooth is in steel not every time. So it's cutting in, and then it exits the cut. It's cooling down, and then again it starts to cut. Have a good big heat inside, but then again going in and going out. So every time it's a hit. So every time it's an interrupted cut. Chip section here, it's a constant. We will talk about chip thickness in the next slides. Here, because of the motion of the feed and also rotation of workpiece material of cutting tool, chip section is different. So it's started from not maximum, so sometimes it's 0. When we talk about full slotting operation, it's going to the maximum in the middle and then going down, and we exit the component with 0 chip thickness. Cutting forces also the same. They can be continuous. They are more continuous and permanent in turning operations. In milling, they are variable. Here, the one cutting edge is engaged in turning operations, and in milling, many cutting edges, so it's multi-tooth tool. And also chip control. When we talk about milling, in most of cases, chip control is not a problem. It's a piece of cake because it's a cutting edge with the contact in the metal is not always. So basically, it's chip generation is very easy, and it's not make a big barriers to the cutting process. It makes when we, for example, we'll talk about deep slotting or pocketing, but not that often like in turning, when every time when we need to think about chip control. If chip will not be divided and will be not small, will be long, it will rotate on the workpiece, and it can damage the tool and can damage the surface, and you will get the not ideal surface finish in the end and tool life. So let's talk about cutting angles. For sure, you can open some catalogs, you can open books, maybe you already opened it in the past in university or in college, but just briefly and very easy way, I will try to explain. This is a turning holder, so it consists of holder itself made of steel, can be different shape, prismatic or modular for external turning, or modular or cylindrical for internal turning operations. And also it contains cutting unit. So cutting unit's a cutting insert basically, which cut. So holder is needed to input this tool to the machine tool. The turning holder can be different sizes, can be different cross section, depending on the size of the workpiece we need to machine, the size of the machine tool. Also, it's connected things. It inserts on this cutter or in cutter in general. It has different cutting edges, main cutting edge and secondary cutting edge here. Also, it has a rake face and clearance face. Clearance rake face, usually chip is going away and in contact on rake face. That's why here we see very big heat generation and also wear generation and development. And the clearance face flank. So on flank, we also face with wear for sure, because this is cutting edge. And basically where it's starting somewhere from here, but also we are measuring it on measuring the wear using the Brinell loop on flank. It has a nose, so it's an intermediate cutting edge between main and secondary one. Also, secondary one should have also rec face and clearance face, or not should, but sometimes it should it should have it, because we need to, if we want this turning tool being used for facing operation. I mean to work in this in this feed direction. So for facing, it's a vertical, perpendicular to exits of workpiece, and for longitudinal turning, it's horizontal. It can be different for copying operation, for example. Inserts have been clamped to holders by screws, or by lever, or by clamp. Also, you can open the catalog, and every catalog, for example, our master catalog, you can download right now if you want. In handout, in menu to the right, I connected 3 different catalogs. One technical brochure, one of the most popular tools, All-Star, and the master catalog, our Bible with all designations, cutting datas, and so on. So in different catalogs, we can find designation of the holder, and the first symbol means how inserts is being clamped, by lever, by clamp, by screw, or by another way. Also, in a lot of cases, cutting inserts is laying on the shim or anvil. Anvil is needed for defense, to defend holder, because holder is more or less important thing. I mean, also in terms of price, we talked 2 days ago about prices in economics of metalworking. So usually we need to save this important holder in order to avoid its breakage earlier than it's expected. So usually tool life of the holder is about 400 indexes or indexing. So indexing means it's indexable insert. Insert can be rotated, it's multi-edge insert. It can be one-sided and double-sided also. And shim is protecting a holder if the cutting insert is been broken or overloaded or by mistake or not by mistake. And next is been to be broken is a shim, or also it's protect from heating, overheating of the holder. Also, I faced several times when in heavy duty operations when the coolant was not applied and the shim was not thick enough, it was a special tool. It was a plastic deformation under. So basically, we need to also to think about shim if we don't apply the coolant, and if heat in general is very high in the cutting zone. So here the cutting zone. As for holders, they can be in different shapes, different sizes, from I don't know, 10 by 10 millimeters to 60 by 60 millimeters. If we talk about prismatic shape, they also can be modular, like KM1s, PFC, and so on. And inserts, cutting inserts can be different: one-sided, double-sided, smaller size and huge size for heavy-duty operations, for tube machining, and so on, and different shapes. Also, they can be rhombic, they can be sharp rhombic, they can be round, they can be square-shaped, and so on. If we talk about turning cutter in general, so here you can see the turning cutter from the past, from the 30s of 20th century. It has 2 cutting edges, like I showed before, main cutting edge and secondary cutting edge. When you cut it, I mean, if you want to cut it, I mean, visually, in cross section, you will see rake angle and clearance angle. So basically, these angles making the cutting edge, I mean, cutting edge itself sharp. And also, they avoid, if they are bigger, they avoid having extra friction between workpiece material, for example, clearance angle responsible for that, and the cutting tool edge. So for sure, if we have bigger angles, it works lighter. It's cut very nice, especially aluminum and soft steels. If rake angle is not big and clearance angle also not big enough, it's a very strong clearance. There's a strong cutting edge and it can be used for heavy duty, for example. Also, there's another cutting angles in different books in your country, according to your country, to standards of your country, local standards. They can have different abbreviations. I mean, for example, here it's eta, kappa, lambda, and so on. So basically, you can find this deeper theory in your books and in English-speaking books also. If we will look on the turning holder, on turning cutter from the top, in the contact with the workpiece material, you can find the two angles. I put here abbreviation kappa. It's a lead angle and also secondary lead angle. Why also I'm talking about these angles? Yes, not in details, but also I'm pointing out their value here, because we can operate them when we use the turning cutter. We can change turning cutter to another geometry, and we can manipulate of lead angles too. So it can be 90 degrees or can be 75 degrees. Also, I'm talking about EMEA and Asia standards. In the US, it's another. It's the same angle. I mean, but it's measuring from vertical position, from perpendicular line to the axis and the line of the cutting edge. In Europe, it's been measured from the axis of the workpiece to the cutting edge line. So it's a lead angle. They can be different, as I said, close to 90 degrees, close to 45 degrees. They can be 60 degrees and so on and so on. So why it's important? At first, it's influence on chip thickness. When we talk about when we are talking about cutting process, for example, the same geometry. I mean, geometry of cutting. I mean, a rake angle, clearance angle, chip breaking profile. We can have on the rhombic insert and also on the square insert, for example, or rhombic with this inclination in the holder. But we can use the same feed, the same cutting data, but in the second variant, when lead angle is 45 degrees, with the same feed, we will get a much smaller chip thickness. So load on the cutting edge will be smaller, but sometimes it can be critical smaller, and it's not desirable. And also it influences on chip control. So basically, when we close to the 90 degrees, chip control is better. When we use the same chip breaker, but with a smaller lead angle, chip control, we need sometimes to increase feed also to get optimal chip control. And also automatically we can increase feed to get the same edge, to get the same chip thickness, in order to put this cutting edge in the same conditions like in laboratory. I mean, when it was this chip breaker for this insert was designed. And to get maximum tool life, to get maximum results. So smaller lead angle, smaller chip thickness, and in most of cases, we are compensating that by increasing the feed FN here. The same is for milling. In milling, in WIDIA catalogs, these feeds, FZ, feed per tooth, is being recalculated automatically depending on the clearance and on the lead angle of the milling cutter. And in the catalog, you will see you will not need to recalculate. It's recalculated in the catalog tables and charts. Also, this lead angle, in other words, it's called approach angle. It's influence on approaching of the tool to the workpiece and on its strengths. So here, for example, when you approach to the workpiece, the sharp, more or less sharp corner will start to cut at first. If, for example, it will be interrupted cut, not like here, but there will be some flats, some severe skin, it will be critical, and it can lead to chipping and other types of wear we will talk tomorrow about. So better to use tools with a smaller linear angle, and not the corner will start to cut at first. The cutting edge which usually is a little bit stronger. Also in chip breaking area, usually chip breakers, they are sharper in the nose, and then in the cutting edge they are a little bit stronger. The edge preparation has been increased a little bit. And also lead angle and secondary lead angle, they important for in geometrical point of view. If you need to machine some interesting shape component, you need to understand if you choose this tool with the geometry, it should be possible to pass through all this way and not touch by insert or by holder the workpiece material. To have it, so this angle, this secondary lead angle, should be greater than the angle on the workpiece, on the component. And also, it's important to know when you open the catalogs, we, for example, are showing in which direction this cutter with the insert can go. For example, here, the cutter can go in horizontal direction, in vertical, and also down. So it has clearance angles and rake angles almost everywhere. But for example, here, you can see the arrow only showing to the left. So it's possible to use it only for longitudinal turning, so only to horizontal direction, not on vertical, because we didn't talk, but usually if you are tool designer, you need to understand that you need to also to rotate, to incline the whole surface of rake face, of the bottom face in the holder. It's on angle, on inclination angle. And here, most likely the inclination in that here there is no any clearance angles and rake angles. So this holder or here, it cannot go vertically. And if we talk about inserts, they also have clearance angles and rake angles. Also, if you open the catalogs, you can see the designation, ISO designation system. So it's international. It's more or less the same, and only in United States it's different. So just sizes, the abbreviation is different. Different digits means the same. So with imperial sizes. For example, length of cutting edge, or inside a circle, also thickness 4.76 if I remember well, but it's better to open the catalog to understand these dimensions. Corner ready, edge honing, and also geometry name, and double-sided or one-sided, and so on. And the shape for sure. And geometry of the tool is a combination of geometry of the insert and the geometry of the holder. And for example, rake angle, why also? Because in the past, these inserts, they had a flat top, and we used special chip breakers, which were clamped mechanically on the top of the same insert, and we could change this chip breaker, bigger one, smaller one, depending on which depth of cut and feed we will use. And this cutter with the flat geometry should have also cutting angles, and it has also axial and radial rake angles and clearance angles. And also today's insert, they also have rake angle and clearance angle, and the combination, so here -5, this +18, results to us 13 degrees of effective rake angle, which will determine the effectiveness in cutting process. The same is for clearance angle. So about these angles we talked a little bit. So also they called back rake or radial rake angle and side rake. So depending on from which size we will look the cross section of cutting edge. So basically, if we have bigger rake angles, and it's very good to use such tools for soft materials and for light cutting, for cutting of the small stock, to remove the small stock from the workpiece. And so-called negative geometry, why negative? Its rake angle is minus, so it's not positive. That's why it's called negative, because in the past, here, like I said earlier, inserts were flat, and the orientation of the insert of the rake surface was negative. I mean, angle was negative. That's why these inserts which I put here called negative, because usually if they have 90 degree between clearance surface and rake surface, you need to incline it somehow in order to have clearance angle, because if you don't have clearance angle, there will be very big friction. So it should be inclined. That's why when we incline flat geometry, the rake angle will be going from 0 to negative values. Cutting forces. When we cut the materials, there is a resulting cutting force, which is a sum of a combination of another ones, axial, radial, and tangential. And they influence a lot on the cutting process. So the main influence is tangential, has tangential cutting force, but also another cutting force is also important. How we can manage with, how we can influence on changing of cutting forces, at least to change main direction of cutting forces. For sure, with the lead angle again. So to change geometry with different lead angles, we are changing the direction of actual cutting force. And I have a small question to you before I go to the next slide. Please have 1 minute about, or maybe less, to open just vote the right variant here with this question, which sounds like, what is a better choice for long shaft turning in your point of view? So long shaft turning, I mean shaft or axle, which has a diameter and the length about 10 times of diameters. So you need to make external turning, I mean longitudinal turning, so decrease the diameter by the tool with a 90-degree approach angle or lead angle, or tool with 75 or 45 degrees, or holder with round insert. What type of lead angle, what type of holder with which lead angle from your point of view is the most correct in this case? So also long shaft means it's not a rigid shaft. So basically it's very, very long. Sometimes these shafts have been used in railway industry, also in engine industries and so on. Okay, thank you. I think we are ready to look at the results, at your results at least. So very nice results. So more or less the same quantity voted for holder with a lead angle 75 or 45 degrees, and also for 90 degrees, approximately the smaller but not that big smaller quantity of you voted for that. So let's talk about it a little bit. So here it's a not rigid long shaft, which has some diameter and the length. Here are the two tools with a 95 degrees of approach angle, and approach angle is 75 or okay 45 degrees it can be. So usually, 1 second, when you apply the first one, axial cutting force will be, it's always perpendicular to the cutting edge line. 1 second, I try to write it. So if you use it here, okay, let's rotate it a little bit. So there is different cutting forces. Here, one tangential is going, it's directed to the screen, and there is a radial cutting forces. There are also cutting forces or axial. So basically, axial cutting force wheels going perpendicular, and it's more or less good. For cutter, it's not that good, but cutter is more or less rigid enough. It's not thin; it's slightly thick. So it's normal direction for the cutting force. But and for material for workpiece, it's not a critical. I mean, here the radial cutting force is not that not that big. But if you talk about 45 degrees, so this combination will direct more to the workpiece. If here it's not a problem, in the middle, if where shaft is not rigid, it can bring additional vibrations. It's if this ratio is about 10 times, it's for sure there will be big vibrations here if you apply this type of cutting tool. It can be correct answer, like some of you answered, if here there is an additional clamp of workpiece. So if it's here, yeah, it is possible to use the inclined cutting edge turning cutters. Also because for all cutting processes, better to utilize chip thinning effect and work faster. But in this sketch, without additional clamping, it's the only choice. Also the same for hole, for long hole. It's a must to use turning cutter with 90-degree approach angle. So we need to balance the cutting forces using the different types of combinations of inserts and holders. So to think about lead angles, to think about component also, is it thin, is it thick, is it rigid, and so on, and also on tooling. I mean on how it is clamped. I mean this workpiece and tool also. If we talk about round, it's a tricky question. If you use the small depth of cut, for example, here it's showed by green color. Depth of cut is small and approach angle will be also small, smaller, and smaller. 1 second. So smaller depth of cut, smaller approach angle, and cutting forces will be directed more to the workpiece, not to the edges. So if you use round inserts, you also will face with vibrations anyway, because in maximal position with this AP max depth of cut maximum, you will get about 45 degrees approach angle. It's not 90, so it's also slightly small, and the resulting cutting force will be directed to the workpiece again and will push it, and it will generate vibrations. Also, the same can be talked about corner of the insert, not round insert, but every insert. With if you use it with the depth of cut smaller than radius of nose radius, you should think also about cutting forces. So basically, they will be directed more vertically than horizontally, and you can face with also micro vibrations and micro chipping, maybe even with light cutting. And so that's why one of the recommendations for usage of turning tools is AP, depth of cut per side, should be greater than radius. So should be third variant, it should be correct. So here, just reminding what's influence on what in designation of inserts. So it's very easy, and also you can look at it in the catalog. Inserts can be also positive and negative. We talk about it a little bit also, because so inserts can be with clearance angle and without. If they are without, we need to incline them to get on tool the negative rake angle. That's why they called negative. So like here, you can see positive inserts we should not incline. It's not necessary because it's geometrically shaped on the insert, and the rake angle can be 0, or if there's a normal chip breaker, it can be according to the rake angle on the insert, the same. So let's talk about cutting data, and we will finish this webinar. So it's just, I hope it's simple enough, maybe too simple for some of you, but we will also plan advanced turning course, but maybe a little bit later. So cutting data, which is related not only for turning, but also for other metal cutting operations. Cutting speed, velocity of cutting, so VC, and number of revolutions, diameter, feed per revolution, so F, feed, and revolutions. AP, depth of cut, Q, it's the chip volume, or in some literature you can see the short abbreviation MRR. Feed rate or speed of feed, so velocity of feed, VF. Chip thickness, we already talked about that, and spindle power and specific cutting force. Specific cutting force, it's a related coefficient to every material. We'll talk about it tomorrow. So cutting data, cutting speed, feed, and depth of cut. Cutting speed in turning operations is a peripheral constant speed or speed of the cutting edge on the diameter of the workpiece. So basically, to understand that, we need to look at the formula, and on the next slide, how it's been calculated also in addition. So cutting speed, it's a multiplication of multiplying of P on multiplied by diameter by revolutions, number of revolutions per minute. And basically, it's a peripheral speed or rotation speed of milling cutter or turning cutter. Also, you can recalculate back and calculate number of revolutions per minute, which you need to apply in machine tool when you know the optimal cutting speed from the catalog of what's called cutting tool producer. So it's multiplying 1000 on cutting speed and divided by P and divided by diameter. And why cutting speed is important? Because if you cut with the same tool workpiece with different diameter, with the same revolutions per minute, this length is being different with the same time. So basically, if cutting edge is here, it will be pushed by material longer. Basically, more material will be going through this cutting edge during with the same time, in comparison with the usage of the cutting tool for smaller diameter workpiece. But cutting speeds and also feeds, they are designed. I mean, they were chosen during the research and development process of the grade. So because they generate heat, the cutting speed generates heat and also pressure to the cutting edge. And every carbide grade, or not only carbide, they designed on the range of the cutting speeds on the thermal and mechanical load. So if we use the same carbide here and here, and not change with the same rotations. There will be different heat here, different heat here, different heat here. Tool life will be different, basically. So we need, and thanks God, in the modern machine tool equipment, it's possible to maintain this in the CNC. So you can see here the length with, for example, diameter, different diameter, 150. It's almost, it's 2 times smaller here than here. Here the difference can be, yeah, just radially 25 millimeters, but here the difference is much bigger, and tool life correspondingly will be different. Also, you can make a practice to calculate it by yourself. And usually here, for example, for facing operation, we need to compensate. You could hear it maybe, I hope, when we go into the center, rotations are increased correspondingly to maintain the cutting speed given by the catalog. And here, compensation is not needed. So according to this diameter, if the catalog recommends this cutting speed value, we should just maintain it. Also, it's possible to do, maintaining of cutting speed, depending on the diameter in CNC, in the G codes. So usually it's a G96, which allow you to maintain cutting speed at 200 meter per minute, with in the range of these diameters. So also you can put additional limitation of maximum revolutions and minimum revolutions, just if you know the capability of your machine tool. Or you can maintain a number of revolutions with the code G97. Feed, it's a distance between 2 positions of the cutter during one rotation. So here it's began and here it's finished. One rotation passed, and you can see you will cut this length of the material, so which equals the FN. So FN is feed per revolution. So it's a determine also chip thickness. If you take a chip, you will here, for example, you can measure it manually and understand, if you know approximately approach angle, you can measure the thickness of the chip and understand which feed was used. And also you can measure the length, and you can understand which AP max was used. And the AP, or depth of cut, it's a distance between, so basically it's the height of the stock is being removed per one pass. So it can be calculated with workpiece diameter and minus diameter of desired shape divided by 2. And feed speed, speed of feed, VF. It can be calculated multiplying feed per revolution by number of revolutions. So it is a distance per minute which has been passed by cutter in a direction of feed, direction of cut. And we came up now to productivity. It's a Q, which is multiplying AP by FN by VC. So depth of cut by feed per revolution by cutting speed. We'll get cubic centimeters per minute. So it's a volume of the stock which is removed by 1 minute. So with the same tool life, the tool which has greater Q value, it's better, it's more productive. And usually it's like a speed. You can calculate the time for component, divide length by VF. You can calculate here the time also. I had not shown this elementary formula, but it's obvious. Also, choosing the tool, we can influence on the roughness, on the surface finish. There are different formulas can be done, but I showed very simple here. Okay, formula maybe not that simple, but this chart is more or less can be understandable. Depending on the radius, corner radius, and the feed per revolution. So, for example, here the next position of this cutter in one revolution will be here, and this height of the metal here is not even. Metal here will not be even. The height will be equal to approximately to array, so to roughness, to quality of the surface we will get as a result. So depending on the corner radius and the feed, you can find that increasing the feed, we will get rougher surface, so not so brilliant. But if you use the same shape of insert with greater radius, not for example 0.4 but 1.6, you need to understand. So, but with the same feed, so this height will be smaller. So basically, if you increase the radius, roughness will be better. But in the same time, you should remember what was said several slides ago. Greater radius, greater part of the cutting force, which directed to the workpiece. So basically, will be with bigger radius, there will be more affinity to get vibrations. So in some recommendations, so what AP to choose? Usually choose AP, how it's recommended in electronic catalogs or in PDF or printed catalogs. But in addition, so it's better to not use AP greater than corner radius, and not to have maximum value not greater than 2/3 of cutting edge length if approach angle is 90 degrees. So it can be smaller because we can use different holders with different inclinations, or not greater than AP max, which is showed in the catalog. Also tomorrow we will talk about chip breakers with the geometry of a chip breaking profile, and you will find this value T. So it's a T length, which basically is it here. Some inserts don't have it, so very sharp ones. But for semi-roughing, for roughing operations, they are. So FN feed per revolution should be not smaller than this T length, or there will be not effective cutting process. And also, feed should not be greater than half of the corner radii. It is because of this. So basically, if we will get a very big feed, maybe it's good for cutting edge. I mean, maybe it's very strong, it's very small, has very small rake angles, and it's good, okay. But roughness, if we have a greater than this value of feed, will be very big. So that's why this recommendation has been put here. Also, if you use according to this recommendation, if you have a depth of cut smaller than corner radii, you will get not ideal chip breaking. So basically, chip breaker they designed better in the main cutting edge, not in the corner. And power, better to use a power calculator in our electronic catalog. So basically, we call it Novo. So basically, it's have inside the database about all specific cutting forces for every group of materials. So steel, P1, P2, and so on, with the coefficient of hardness and so on. And it's calculating power, a tool which is needed to be provided by machine tool. Finally, but very approximately, but it's very approximately. If you don't have any electronics with you, I hope there will not be such a situation. It can be calculated slightly easily. So multiplying of cutting data, or dividing of cutting data by the coefficient 12 on stainless steel, 20 on steel, 25 cast iron, and about 100 for aluminium. You'll get kilowatts, which is needed, which are needed to be provided by machine tool. So here, shortly, we finish the first part. Tomorrow we will continue with the second one, when we will touch insert geometries, chip control, chip breakers, carbide materials, workpiece materials, and problem-solving types of wear, and how to avoid the wear which we don't want. So we are ready to have questions from you. I see that a lot of questions are ready, but cannot read them now. I hope Isabel can help me now.
Yeah, sure, Vladimir. Before starting the questions, I just wanted to ask you if you can share our Advances 2020 catalog and show our latest turning products to the audience also, like the WGC, because I think that is really interesting to them too.
Maybe tomorrow you want to do it now.
Okay, we can do it tomorrow. Yeah, actually, we do have a lot of questions.
Yes, but it will be 1-2 minutes. I need to upload it to the webinar, and the auditor can download it. But better for everybody, I think, to connect tomorrow if you have time for sure, and can download it from there.
Okay.
Maybe I will try to show it briefly now. You can ask me another question, and I will try to open the catalog during this time, and we'll show it.
Okay, fast. So please specify the parameters to be considered in turning of aluminum LM25.
Oh, sorry, you cannot hear. Just muted. So I just asked what parameters is interested to know: cutting angles or cutting data? Because if to talk about cutting data, it's very easy. You can open also the catalog, but usually the feed, depending on the insert and insert size, the feed can be around 0.2, for example, 0.25, or for finishing 0.1 per revolution, and speed can be from 300 to 800 even meters per minute, because aluminium can be cut very easy. But this grade of aluminium, I'm not familiar with. Maybe it's a special grade with a lot of silicon inside, maybe. So I need to check the grade, and I can get back to you according to your email, but a little bit later, just to check what the grade of aluminium was in your question.
Okay, great. Another question for you is, please explain how to calculate the cutting forces spindle power.
For cutting forces, also right now I don't have a formula for that, but basically I partially answered to that here. 1 second. In the last presentation. So torque and power tool, better to use automatical calculators. But if you don't have very rough formula, it is here. So it's multiplying depth of cut, feed, and cutting speed between them, and divide by coefficient depending on the material. So I'm using, for example, not because I cannot memorize this specific cutting force coefficient. Yeah, it can be said that it's here under the cutting data showed in the formula, but better to rely on the catalog and to see it there. So the same is for cutting force, but I need to find this formula. There are different formulas depending also on cutting data and on material and coefficient of machinability of this, but I don't have here it right now in the presentation. So also I need to to come back to this question later.
Sure. And Vladimir, is WIDIA coming up with prime turning inserts?
Frankly speaking, we had something. I mean, we still have it. 1 second, I will try to open the catalog and to show it. 1 second. But our big catalog, it can be opened here. Also, you can open it in handouts. So master catalog. We have a geometry called specifically designed for better cutting in vertical direction. As if to talk about prime turning, yes, we understand that it's like a back turning, if I remember well, this technology from another producer. So here, basically, maybe not now. So for future, probably yes, but not now. So because also it's very good sometimes, but only sometimes, because effect of it is not that great. So basically, if you go from the right to the left, it's almost the same effect if you go back. So 1 second, I will try to find this this geometry in the catalog. I will share now the screen with our catalog. So basically, it's our insert sizes and shapes with different geometry. For example, DNMG inserts with a Viper, also cutting. Yeah, CT. So we have this, for example, inserts CT. You can see here. I'll try to magnify somehow. So it's a very open cutting edge profile and chip breaker profile here. This insert can be used for back turning and can be used for it's a PDF, I cannot write it here. So it can be used for if you have a facing operation, for example, here you need to machine vertical shape. It's not necessary to go from the outside to inside the workpiece if here the axis. It's possible to go here and go down, and this additional chip breaker, they are they're shaping the very good chip, so it's not long. It's so it's more or less the same technology which WIDIA introduced about 20 years ago. So here's our catalog. Also, the system for our catalog is this very similar. Here, for example, you can see on which pages there are holders, different holders, cartridges, cutting data, information about chip breakers, about grades, inserts, and also holders. Holders can be different. 1 second. Yeah, for example, here's holders for internal turning with a 90-degree lead angle. Also, the additional angles showed. I mean, these rake angles, axial and radial. It's in addition, for sure. Sometimes it helps, but better to look at the arrow and to look at which direction it can cut. I mean, cutting holder with the insert for sure. And here the spare parts also showed, and for which type of applications can be used. And designation of holders and inserts also in the insert chapter of this book. So if you have more questions.
Yes. How do you calculate the power and feed with respect to material hardness?
Again, it's better to use our electronic catalog. I will try to maybe open it now. because there is a place when we put a hardness, when we choose, when we are choosing workpiece material. Here in this simple formula, what I showed earlier, yeah, it's hard to do. So it's just plus minus 25% of tolerance in this very easy to use formula. So basically, you need just to decrease cutting hardness according to the difference of average cutting hardness of steel. So it's about 220 Brinells, and hardness you have, for example, 350. So divide first value, I mean 220 by 350, and this coefficient, oh no, or vice versa, sorry, 350 by 220, and multiply this coefficient. 1 second, I will show presentation again. And multiply this coefficient for steel or for cast iron to this coefficient. I mean, dividing of hardness you have by hardness by average hardness. So 1 second, I will try to check to find cutting data. Maybe you can ask another question meanwhile.
Yeah, Vladimir. Let's do the last one. So then we can close because we are already over time. And then I asked the other people to please send us the questions to our email, the email that you received as a confirmation, or I don't know, anything you want to ask us, and we will answer you. Can you kind of explain the cutting fluid influence, Vladimir?
Cutting fluid influence, it's depends how to explain it. What exactly is needed? Yes, cutting fluid can be different. It's a lot of oil with not a lot of oil with different effect. It's a coolant effect and also oiling effect, which decrease the friction. So basically, for different materials, we can use different cutting oils. For example, for steel, it's just also it's better to ask cutting oil producers for cutting. So, for example, for stainless steel materials, some recommend another grades of oil, brands of oil or models of oil, which have a good resistance to build-up edge, for example, for turning. But basically, coolant is decreasing the temperature, and for turning, it's a must to have a to use this fluid with a maximum pressure, if possible, in order to decrease the temperature, because it's higher than in milling. Because in milling it can cool down if even without coolant, cutting edge will be cooled down. And in turning, usually it's not possible, and that's why we use the coolant every time. Which kind of coolant? Usually it's 5-7% dissolution in water. So basically, also there are another recipes, but better if you need in addition these recommendations, we can prepare some short webinar for kind of cutting fluids too. Yeah, in the past, WIDIA had cutting fluids in the assortment, but yeah, unfortunately not now. That's why we need time to have a more detailed answer to this question. In the past, we recommend some grade of fluid, WIDIA cool, so, but not now.
Fantastic, Vladimir. So I thank you for all of your questions and for your attention during this webinar. And
here I'm showing electronic catalog. Yeah, sorry, it's another language, but anyway, you can see here the choice of material during the cutting data calculation by our electronic catalog. And here you can see it is possible to choose not only group of material, but also of material according to the standard, and also to change the hardness. So to put a higher hardness if it needed, Brinells, for example. And it will be used for recalculation of power. So here, for example, 11 kilowatts they need for this AF new air steel. harder still. Yeah, that's what I wanted to add.
Okay, great, Vladimir. I think there is also some suggestion that they would like a novel training, and I think that is absolutely possible. So we will put it in your wish list for the future. Tomorrow we will show you more about the catalogs and about Novo. Vladimir will just give you a few quick tips, and please join us tomorrow for the second part. And thank you for being here with us today.
Yeah, thank you, and stay at home.
Bye bye.